All right, so for this lecture, this is a continuation of constraint optimization. Last time we solved this problem here. Essentially, we're trying to figure out how we would go from our colony to the trading post with the shortest distance. Therefore, we got to pick the correct door to pick, all right? So we're going to continue with constraint optimization. And today we're going to cover a different idea called duality. Duality. So we previously learned the KKT conditions, which given some minimization problem, right? We have some kind of inequality constraints like this and equality constraints. And you will use the logics from the KKT condition, which are the stationary condition, primal feasibility, dual feasibility, and complementary slackness. By using these four logics, you can logic your way through to get the solution. Okay, that's basically what we did, and then we applied to a bunch of word problems that to see how they're used. So let's return to our initial optimization problem we've done many times. This is the one where we trying to find a rectangle that maximizes the area while constraining to 20 miles perimeter, right? So 20-mile perimeter, maximizing the internal area. After we turn it into a Lagrangian, it looks like this. And we basically learn how to solve this problem using the KKT condition. Okay, but instead of trying to solve this using the KKT condition, there's a second way you can do this. Right? The second way is potentially simpler and it's equivalent. We call this the dual formulation. Dual formulation. Oh, so we call the original problem the primal, and we call the alternative dual formulation. So this is the primal. This is what we try to solve. And we can actually convert this into a different problem, which if we solve this problem, we can get the exact same solution. Okay? So I'm going to define D as a set of all possible solutions. So out of all the possible solutions, we define the dual objective as when you solve the Lagrangian only for x, right? So we're not solving for lambda or gamma. We're only solving for x. So if you find the x that makes the Lagrangian as small as possible, that is the dual. The key is to realize that here we're only optimizing x and not lambda and gamma. Given the example above, like here, right? If we want to take derivative only with respect to x, so if you take derivative here, with respect to x1, then that's going to be minus x2 and 2 lambda. Minus x2, 2 lambda. If we take derivative with respect to x2, so that goes away, then it's x1 and minus 2 lambda. Okay? So if we take derivative only with respect to x, and we don't really worry about the lambda and the gamma, we end up with this expression. Well, this expression tells us that x2 is equal to minus 2 lambda, and x1 is also equal to minus 2 lambda. So now therefore we can, this is the solution. The optimal solution for x1 and x2 is simply minus 2 lambda. So now that we know the optimal x solution, we can plug x1 and optimal x2 solution. We can just plug the solution into the original problem. So original problem. So we now plug it in. So this is x1, this is x2, and over here is x1, here's x2. So we plug the solution in here, and this creates the dual problem. So over here is a dual. This is it. Now, with a dual, it kind of does the opposite as the primal. With the primal, we're trying to minimize. However, with the dual, what we do is we try to maximize it. So we're trying to maximize this objective. And let's look at the constraint. The constraint is saying that 2x1 plus 2x2 is equal to 20. So it means 2x1, x1 is minus 2 lambda, plus 2, x2 is also minus 2 lambda is equal to 20. This implies that the primal constraint is minus 4 lambda plus, well, minus 4 lambda again equal to 20. So that's minus 8 lambda is equal to 20. Right? Minus 8 lambda is, therefore it's 20 plus 8 lambda is equal to 0. So this is the constraint, right? If we plug the optimal solution into this constraint, we got a new constraint. So this other constraint is the dual constraint. So now that we have the dual, here is the constraint for the dual. 20 plus 8 lambda, right? So when you convert from primal to dual, you simply convert it from minimization to maximization, plugging in the optimal x solution. So we found the optimal x solution in terms of lambda, and after we plug it in, now we can write the dual formulation. So we maximize the dual formulation, and then we also define the dual constraint. Okay? Once we have this, then it's pretty easy. It's pretty easy to solve this. Like over here, this is the constraint, right? So this is the dual formulation, and over here is the constraint. Once you see the constraint, we know what lambda is. What is lambda? Lambda is simply 20 equals to minus 8 lambda. Therefore, 20 divided by minus 8 is equal to lambda. So now we have lambda, right? Then once we have lambda, it's pretty easy to solve this because we know exactly what lambda has to be. So if we know lambda, right? Notice how if we know lambda, we know x1 and x2. So another way to essentially solve the original formulation. Right? We could rewrite the primal. This is the primal objective into the dual objective, and in the dual objective, notice that it's very easy to find lambda, and that's the purpose. Sometimes the primal could be easier. Sometimes the dual could be easier. And after you do the conversion, you can pick and choose which one is easier. Okay. Now let's solve the dual, and if you get the same solution, right? So over here is a dual, like I just told you. Because of this relationship, we see that the lambda is equal to minus 2.5, right? Therefore, we now know minus 2.5. Then if we plug minus 2.5 into this, then we get x1 and x2 is equal to 5. So this is the identical solution we got previously, because remember the perimeter of the walls were 5 by 5 by 5, right? And this observation tells us that constraint optimization problems, we can solve all the variables together. We've seen that. We can convert the problem into dual, where the variables are the Lagrange multipliers. And in many cases, it's easier to solve it once we convert it into the dual. The dual formulation, the third observation, is that the dual formulation is always the opposite of the primal formulation. So if you're trying to minimize the primal, you try to maximize the dual. Or if you're trying to maximize the primal, then you're trying to minimize the dual. So what's happening is that the dual actually always looks like this, while the primal looks like this. So in primal, you're trying to go as low as possible, so minimize. In dual, you're trying to reach the same solution to reach it. Okay. Now you may be wondering, well, remember wondering why there's this like opposite relationship. The reason why there's an opposite relationship is that the definition of the dual is that you simply pick the x that makes it as small as possible. You pick x that makes the Lagrangian, and you don't deal with lambda and gamma. And the definition of Lagrangian is this. So we know the definition is the function plus the equality constraint and the inequality constraint. Now, when you find the optimal star, we know that the equality constraint must be satisfied. Therefore, that's the equality constraint must be satisfied. So when it's equal, then equality constraint is equal to 0. So this is not true. Implying that this right here can only be negative. Inequality constraint, remember, um, the compl- uh, the due to the complementary slackness, right? They have to multiply to be zero. So this could either be zero or it could be a negative value, right? So um, is that true? Yes, yes. This is either. Therefore, this right here tells you that the dual is always less than the function itself, right? This is because if you have a function plus some negative value, therefore this has to be less than the function, right? If you have this and this is negative, then this has to be less than this. And therefore, this is how we know that the dual is always less than the function itself. Like this. Here's the dual, and here's the function itself. That's why the shape looks like this. Okay. Now, the best way to do this is really just to try yourself. I want you to pause the video at this point. So pause the video. See if you can follow the steps. Convert it into a dual. Right. Solve it first with the regular KKT condition, and then solve it with the dual. Once you solve with the dual, they should be the exact same solution. I wrote the solution for you. So the KKT solution, the dual solution. And once you're done with that, also solve this problem. Okay, so this will give you lots of practice. And I also wrote the answer. So once you've done both of these, you are now ready to tackle putting everything together. So the Boston colony, right? The Boston colony, this is the Northeastern colony. This is the MIT colony, MIT. And the Boston colony is here. So our biggest trading partner is MIT, but there's also another colony called the Boston colony. Trades with our colony by jumping on the green line. So they jump on the green line. This right here is the green line. So they jump on it to basically reach us. However, after they jump on it, they still have to jump off the bus to reach us. Therefore, they need to know exactly when they need supposed to jump off. Okay, so let's say the center of city is 0, 0, and we can describe the green line as this. So here's the green line. Due to our trading relationship with MIT, we constructed our door right here. So this is our door because this was the closest to MIT trading. Therefore, and our door is at this location. Therefore, what is the XY coordinate that a person will have to jump off the green line? Like jump off the green line to minimize the walking distance to our door. Okay, so where do they jump off to minimize the distance, right? I want you to see if you can formulate this problem and then solve it with the KKT condition and then solve it with the dual. And then you can use NumPy to essentially double check your solution. So the trade point with MIT, so over here is 4, 6, right? So once you solve this, see if you can solve the XY coordinate. A person will have to jump off in order to minimize the distance to trade with MIT. So they have to trade with us, which the distance will probably be here, and they also have to trade out with MIT. So what is the location they need to jump off when they trade with us versus trade with MIT? See if you can solve with the KKT condition. I solved this for you, so this basically tells you the optimal location that minimizes the distance. Okay, so this is the video on the duality, and hopefully you got it. See you next video.